Hi, my name is Yarden, and I'm going to teach you guys about integral tests and estimates. So before we begin, we should go over the conditions of doing an integral test. So first things first, you need to make sure that f of x is continuous. You also need to make sure that f of x is a positive decreasing function from 1 to infinity. When you do the problem, a sub n is equal to f of n. So here are the possible outcomes of integral test. If the integral from 1 to infinity of f of x dx converges, then the series of a sub n from 1 to infinity is convergent. If the integral of f of x dx from 1 to infinity diverges, then the series a sub n from 1 to infinity is divergent. Now that we have gone over our basic conditions and outcomes for the integral test, we can begin. So let's say that we have the summation of 1 to infinity of 1 over n squared plus 1. First thing you need to do is convert that a sub n to f of x. So we get that f of x is equal to 1 over x squared plus 1. F of x is continuous, positive, and decreasing from 1 to infinity. So that means that we can continue on with the integral test. We can convert our original summation to be the limit as b approaches infinity of the integral of 1 to b of 1 over x squared plus 1 dx. You should recognize now that 1 over x squared plus 1 is the derivative of the inverse tangent function of x. So that means that we can now integrate this problem to be the limit as b approaches infinity of tangent negative 1 of x from b to negative 1. So now we're going to plug in those two values into the equation and then subtract them from each other. So that we get the limit as b approaches infinity of the inverse tangent of b minus the inverse tangent of 1. Now, the inverse tangent of infinity just happens to be pi over 2, and the inverse tangent of 1 is pi over 4. So then we get pi over 2 minus pi over 4, which is equal to pi over 4. So then we can conclude, because the integral of the function converges, that the series converges by integral test as well. Now that we got this simpler problem out of the way, let's try and do another more complex problem. So here we have the series from 1 to infinity of the ln of n over n squared. So first thing we want to do, like every time, is convert the original series to a function so that we get that f of x is equal to ln x over x squared. F of x is continuous, positive, and decreasing from 1 to infinity, which means that we are allowed to use integral test for this problem. Before we begin, let's convert the summation to an integral. So we're going to get the limit as b approaches infinity from 1 to b of ln x over x squared dx. We're going to have to integrate this equation by parts. So let's choose ln x to be our u and x to the negative 2 as our dv. So once we integrate it, we're going to get the limit as b approaches infinity of negative ln x over x plus the integral from 1 to b of 1 over x squared dx. Once we integrate this new problem, because of integration by parts, we're going to get that the full integration is the limit as b approaches infinity of negative ln x over x minus 1 over x from b to 1. We're going to plug in those two values and subtract them from each other so that we get that the limit of b as b approaches infinity is negative ln of b over b minus 1 over b minus negative ln of 1 over 1 minus 1 over 1. The negative ln of infinity over infinity is equal to 0. Negative 1 minus infinity is also equal to 0. 0 over 1 is equal to 0, and 1 over 1 is equal to 1. So this integral is equal to 1. Now, because that the integral converges, we can now conclude that the summation converges as well by integral test. Now that we know how to use integral test, we can now find the remainder estimate from integral test. So this is what you need to know. If the summation of a sub n converges by the integral test, and r sub n, which is our remainder, is equal to the true sum minus the sum from some number, then our remainder is going to be greater than the integral of f of x from n plus 1 to infinity, and is going to be less than the integral of f of x from n to infinity. Now let's do an example problem. Here we have, if you use 10 terms of the series from 2 to infinity of 1 over n times ln of n squared, how accurate would your estimate be? Now, just like last time, we're going to have to use integral test first, but instead of testing it from 1 to infinity, we're going to test it from n to infinity. So we can convert our original series to be that the limit as b approaches infinity from n to b of 1 over x ln x squared times ln x squared dx. We're going to do some u sub here, so u is going to be ln x and du will be 1 over x. Then we're going to get the limit as b approaches infinity of the integral of 1 over u squared du. The integral of that is going to be equal to the limit as b approaches infinity of negative 1 over ln x after we plug in ln x back to u from b to n. Then once we plug in those variables, we're going to get negative 1 over infinity minus negative 1 over ln of n, which is just equal to 1 over the ln of n. Back to our original equation of this, we can now plug in f of x dx to be 11 and 10, and that the remainder is going to be of 10 as well. We found the integral of f of x, so now all we need to do is plug in that 11 and 10. So then we're going to get that the remainder is going to be less than 1 over ln of 10 and greater than 1 over ln of 11. Hope you guys learned a lot from this little short video. Good luck on the final, and thank you for watching.